Hey everyone, this lesson is all about titration, which starts getting back to the ideas of concentration, and specifically concentration of acids or bases. This is an incredibly useful concept because if you happen to be working in a lab and you happen to be working in a lab that doesn't label their chemicals very well and you spill a jar labeled HCl, you might be in not much trouble at all. Maybe it's like 0.01 molar HCl and it's not very strong. Or you might be feeling pretty uncomfortable because maybe you just spilled some 12 molar HCl. You don't know. The process of titration is going to allow you to be able to figure out what the concentration of an unknown acid or base is by using a known concentration of its opposite. So if you have to try and write a succinct definition, what I'll say is that titration is a lab process, and it's going to take advantage of neutralization reactions, knowing that combining an acid and a base creates water and an ionic salt. So lab process that uses neutralization. And we're going to do that for the intention of knowing the concentration of an acid or a base. So lab process that uses neutralization to determine an unknown concentration of an acid or a base. And visually, this is what's going on over the course of a titration. You may start out with some unknown acid, like HCl of unknown concentration. What you're going to do, not necessarily with a pipette, with a more refined instrument known as a burette, you're going to start dropping base into your solution of acid. Yes, you can make all of the terrible jokes that you want. It just is what it is. So we're going to be adding base to our acid, and as the base interacts with our acid, we're going to start creating neutral water. So as we add base to this unknown concentration of acid, those acid and bases will start kind of canceling one another out. And at some point, we will have added enough base to neutralize all of the acidic molecules within our original sample. So we will have taken as many OH minus ions as we needed to cancel out as many of our H plus ions that were originally present. How do we know when they've all been canceled out? Well, chances are you're going to either use a pH probe to tell you that you're at a neutral pH, or if you don't have access to that, you're going to use some chemical indicator that's going to change color as soon as you've hit a neutral pH. And oftentimes, you're going to use the indicator phenolphthalein. And as soon as it turns a light pink color, you know you're inching into its color change range, which, yes, is a little above neutral, but we make do with what we've got. So here's an old Regents question that has to do directly with titration. So again, this process of either adding a known concentration of base to an acid or vice versa to try and figure out how much it's going to take to cancel out all those H plus ions. So in this particular titration, a student has placed 25 milliliters of HCl, and that's of an unknown concentration. So we have some unknown concentration of HCl. They're going to add 4 drops of phenolphthalein into the solution in the flask, and it's going to be colorless because it's in an acidic solution. The solution is titrated with 0.150 molar KOH. So we know exactly the concentration of OH minus ions in what we're adding into our flask. And we add until it appears a faint pink. So phenolphthalein is starting to change color. We know we must be complete with our OH minuses canceling out our H pluses. And it takes 18.5 milliliters of KOH to make that change. All right, so first let's just look at what chemically is going on inside of that flask. We have a sample of HCl, we're adding KOH, and a neutralization reaction is going to occur. Remember, neutralization just takes the H plus from the acid and the OH minus from the base to create H2O or HOH, and just combines your 2 remaining ions to form a salt, KCl in this case. If we want to know the concentration of the acid, though, we're going to need an equation from table T. So this is directly off of reference table T. If you look there, you'll find it right in there on your page. And I like to call this the MAVA equals MUBA equation, in that your molarity of your acid, Ma, times the volume of the acid, Va, is going to be equivalent to the molarity of the base times the volume of the base when the titration is complete. So this represents a completely neutralized solution. Really, if you go through and do the math, what it's saying, molarity times volume is equal to moles. If you go through and look at your units, moles per liter times liters is just going to leave you with moles. So the amount of H plus, moles of H plus, is going to be equal to moles of OH minus if the solution is neutral. And that's what this titration equation allows us to do. So let's go through and do that calculation for this particular example. I need to make a little laundry list of what I know and what I don't know. So I'll tabulate all of that here. Molarity of H plus, so concentration of the acid. My acid was HCl, and I have absolutely no idea what its concentration is, so that's going to be our X. Volume of acid, well, I had 25 milliliters of HCl, so this is going to be 25.0 milliliters. I don't really care what the unit is, whether it's milliliters or liters, as long as I stay consistent with my acid and my base. The base, on the other hand, I did know the concentration of. I know it's 0.150 molar, so it's a relatively weak base that I'm adding to titrate my acid. And it takes 18.5 milliliters to completely neutralize the 25 milliliters of acid. If you pause for a moment here, just taking a step back and thinking about what these numbers mean, it took slightly less base than there was acid to completely neutralize the acid. That must mean this base was a little bit stronger than this acid in order to neutralize it with less. So if it had taken 25 milliliters of base to neutralize 25 milliliters of acid, that must have meant they were the same strengths, they had the same concentrations. Because it took slightly less base, that must mean this base is a slightly higher concentration. So there was more OH around than there was H+. So it didn't take as much to get them to be equal. But that'll just sort of be used as a way to kind of check our answer. Let's just plug it in and do the math, see what we get. X times 25.0 is going to equal 0.150 times 18.5. We can plug that into our calculator and let it do the work for us. When I do that, what I end up seeing is that X times 25.0 is going to be equal to 2.775. Dividing both sides by 25.0 gets me to X equals 0.111 molar. And just as predicted, our acid is slightly less strong than our base because it didn't take as much base to completely neutralize all the H+ ions that were in this original 0.111 molar solution. I want to draw your attention to what is the number one mistake related to titration problems. And if I'm looking at this, what you might be tempted to do if something is asked to determine concentration is use the molarity equation. But let's take a look at this thing. In order to solve for molarity on its own without using this MAVA equals MUBA situation, we need to know the moles of solute. So this would be related to our HCl. At any point, are you given any information about the number of moles of HCl that you've got? All I really see is that I've got 25 milliliters of some sample. There is some information about KOH, but that's not the compound I want to know the molarity of. So there's no information whatsoever about moles of solute. You can try and plug in 0.025 for liters, but it's still not going to get you anywhere because molarity is what we don't know. So there's no circumstance where you can use the molarity equation to calculate concentration in a titration scenario. And you're always going to be given a giveaway to use the titration equation. And that's either the word titrated in the problem, something is completely neutralized, that phrase is another giveaway if you say completely neutralized, or just the fact that an acid and a base, two different compounds, were mentioned in this problem, both needed to solve it. All right, so keep your eye out for clues to use the titration equation to figure out concentration.